All right. Well, let the record state that I'm not going to fall on my face. First of all, that I did start class on time. I was passing out tests. Okay. And everyone here has received his or her test, right? Who is everyone? 2, 4, 6. Oh, we're at 50%. Jeez. Man. Did I say something bad? And we get a new projector. So, looks kind of fuzzy though. Does anybody have any questions about anything before we start? Okay, where we're at, we're in thermodynamics, and we've learned a bit about what the first law is, what enthalpy is, and doing some calculations for that. Now we're going to go into talking about enthalpy a little bit more. So some things about delta H reaction, the enthalpy change of a chemical reaction. If a chemical reaction is multiplied by some factor, then delta H reaction is also multiplied by the same factor. Not surprising. If I can go 30 miles on a gallon of gas, I can go 60 miles on 2 gallons of gas. And I can go 15 miles on a half a gallon of gas, right? So whatever it is, you're doubling, tripling, that the delta H goes the same way. If a chemical equation is reversed, delta H reaction changes sign. So that means that the energy absorbed by plants in photosynthesis to form glucose is then released when glucose is burned. Right? So the same amount of energy you put in photosynthesis is the same amount of energy that you get out when you burn sugar. Makes sense? And the last one here, this is known as Hess's law. If a chemical equation can be expressed as a sum of a series of steps, then delta H reaction for the overall equation is a sum of the heats of reaction for each step. So, for instance, in this example, if you have these two equations, A plus 2B makes some intermediate C, and that intermediate C decomposes into 2D, and you can add these, and there's 2 heats of reaction for each of these steps. You can add them together and get the overall reaction there, the overall heat of that reaction. That's known as Hess's law. And I will show you how to do this in an example. But does anyone have any questions at this point in time? All right, here's Hess's law. I like Hess's law, but most people hate it. But I like puzzles. That's the thing, is I like solving puzzles. So Hess's law is good for my puzzle-solving things. So what is the heat of reaction for the formation of propane? So 3 carbon plus 4 hydrogen forms propane. And we want to know what the heat of reaction is for this. We don't know what it is, but you go and you look these up in the library, you find these 3 equations here. You're like, okay, well, I know these and I can figure out the heat of reaction for propane. There's an old saying that goes, a day in the library can save you a month in the laboratory. Meaning if you go to the library and look stuff up. And now, right now, you're in a academic environment, and you're learning the stuff, and this is an intro class, and you will be provided with all the equations. If you were doing this for real, for your research project, or if you're working for a company, you would have to go to the library, you have to look these up, and you have to figure out which ones you need as well. So we're not going to do that, though. You're going to have everything provided for you at this point in time. But just so you know, you can go to the library, and some of these things you actually legitimately have to go to the library for, because you have to look up the data in old books. Not everything is online. It's getting to the point that everything's online, but not everything is online. The other thing is that you can use library portals. So if you go and you connect to a Wi-Fi network in the library, you can get access to more journals. So that's the other thing is that nice about, you might actually bring your computer to the library and then look stuff up. Okay, so when I look at these problems, what I do first is I think I want to put all the reactants on the left and all the products on the right. So if I'm looking at these equations right now, and this first one, so my logic is I see C3H8, and it's over here. So I already know I need to flip this equation, meaning so I'm just going to go ahead and write 3CO2 plus 4H2O yields C3H8 plus 5O2, and I'm going to do minus H1. You see what I did there? I just flipped it around. And the reason why I flipped it around is because propane is a reactant here and it's a product here, so I need to make sure that the propane, the C3H8, is on the right side of the equation. Does that make sense? So, okay, and the next one, the next two, it's fine. I can leave them as is. Carbon plus oxygen makes CO2, and 2 hydrogens plus oxygen makes 2 H2O. And so I'm just going to leave these as H2 and H3. So how many carbons do I need? I need 3 carbons. So this one here, I'm going to multiply by 3. So I have 3 carbons, 3 oxygens, and 3 CO2s, and then 3 hydrogens. I'm sorry, H2, I'm sorry. 3 H2s. I see H2 and thought of hydrogen for a second. So everybody understand that step. And sorry I'm going through this in great detail. Does everybody get that step? Why I multiply by 3? I multiply by 3 to get the 3 there because there's only 1 here. Is that good? Okay. And then the last one, we have 2 hydrogens and 4 hydrogens there. So we have to multiply the bottom one by 2, and in doing so, we get 4 hydrogens, 2 oxygens, and 4 waters, and 2 there. Is everyone okay with that step there? Okay, now the next thing we do is we add these together. And so notice then that the CO2s, the 3 CO2s, cancel there. The 4 waters cancel there. So 3 plus 2 equals 5 oxygens, and the 5 oxygens cancel there. And so I'm saying they cancel. So instead of like imagine if I have y plus alpha equals x plus alpha. You can just cancel those, right, in an algebraic equation, right? So if you see each side, 3 plus 2 oxygens, 5 oxygens cancel with these 5 oxygens. These 4 waters cancel these 4 waters, 3 CO2s cancel with these 3 CO2s. That's what I'm doing there. And then adding them together, I'll just move this. Adding these together, I get 3 carbons plus 4 hydrogens yield C3H8, and I get 3H2 plus 2H3 minus H1 as the heat of reaction. So then now I take these data and I put them in. So 3H2, 3 times minus 393.5 plus 2 times H3 minus 483.6 minus a minus 2043. And what does that equal? 3 times minus 393.5 plus 2 times minus 483.6 plus 2043. I'm getting minus 104.7, minus 10.7 kilojoules. Okay. Yep. All right. And there's the answer. All right, so recap with this one. This is Hess's law, and I like this equation. I like this example because it shows all of them. So this one here, you flip the first equation around, change the sign of the delta H. These two you have to multiply by certain factors. And the way I look at this is to get the proper number of the so there's only one product here, the C3HA, and then the reactants, get them put in their proper formulas: 3 for the carbon, 2 for the hydrogens. Now the other way you could solve it, then you add them up all together, and you notice that the intermediates, they all go away. The other way you could attack this problem is you could look at this. You could start off with the burning of glucose, propane, burning of propane, and then you could look to get rid of the other things. So, well, you still need the reactants, but when you write these, I could logically attack this problem saying, I want to get rid of this water and I want to get rid of this carbon dioxide from this equation. How do I do it? Well, I need 3 carbon dioxides for that, and I'll multiply the bottom one by 2 to get rid of the water. So you could also equivocally analyze the problem that way. So if you want to do it that way, that's totally fine. I just, in my thinking, I usually think in reactants, but either way will work. So, questions with this one, how to do it? This is nice. It's nice and bright, so I can leave the lights on. Okay. Now it's your turn. I want to know the heated reaction for N2O, so dinitrogen monoxide plus nitrogen dioxides makes 3 nitrogen monoxides. I want to know what it is, but I do know, I don't know that, but I do know these 3 equations. 2NO plus oxygen makes 2NO2. N2 plus O2 makes 2NO. And 2N2O makes nitrogen plus oxygen. 2 nitrogens plus 1 oxygen. And those reactions there. So, using those equations, can you figure out the top one's heated reaction? So where do you start? You put all of the N2Os and NO2s on the left, and you put all of the NOs on the right. If they're already there, you don't have to rewrite the equation. Then you have to figure out what numbers you need to multiply them by. Is anyone getting stuck? Raise your hand if you're just completely stuck. I do want you guys to work on this because students usually have issues with Hess's law. Anyone need help? Raise your hand. Nope. Okay.
Yeah. You have to change the original equation to match the final equation because there was so basically, you put the 2 and the 2 on the left side in the second equation, and then do the balance out in the first equation.
Yeah, you can just whole thing by 2 in order to get the 2.
So there's 2 on 2 and no 2's on the bottom, but only 1 on the top. Sorry, show you. 2 and no 2. 2 the second equation. See, no 2's, there's 2 right here, and only 1 right here. So you have to multiply this by 2. Oh, so you'd reduce this one, not make this one.
Yeah, you want to make the 3 match the one.
Okay, not the other way around. Okay. So divided by, times it by a half. So that would just be 1. What would become half of 2?
Just 1 again.
Yeah, and then it kind of works itself out.
That should. Yeah, because the very last one, I think you also divided it.
Okay. That's it. Okay, first put this on this side.
See, those 3 equations together should match up. Yeah, I think it's
So this is right, and you're given. So this is
yeah, the two oh, 1 out. Yes. Yeah, because then we add the yeah, so. Oh, okay. Sorry, I'm just learning myself. So yeah, those
you don't know what the numbers to multiply the equations into, but the way I'm going to try to see there's two equations here. So
I'm sorry, okay, the one.
side. So
Two. So I'm doing that. So I'm going to the one side. It's the chicken nuts.
and then the options here.
So this would end up being 4, 8, 4, and
Then you add them, take this and you add it up. You get this. So 2 and 2, 2 and 2 0, 2 exact 2 is equals to 6. Now you can
Sorry, I just wish I could further on it, so. These will be the one that will cancel this one here. These two, these are going to cancel. It's the same thing that you did for all of these. No.
Yeah, no,
So
sorry.
this is just a negative. It's going to be 1/2 of negative 1/2. Oh. Sorry, I'm just making sure everything matches. Oh, 2, 2. Oh, there's not even
So do you get the logic? Yeah. Well, exactly. So the logic part to the right, and then for the multiplications there.
this is kind of key for property of writing down.
Easier the equations are able to do.
Okay, so yeah, this is
this thing comes over, these two cancel, I will use the cosine. So these two cancel. These two.
this here.
You struggle. Teach.
So then you can have 1 plus 2 is 1 and 2 and that's 3 cancels.
So it's gonna be 1, 2.
You set which one to multiply, which equation to write which way.
Would you like this? I don't understand this.
Okay, why divide by 2?
Oh, sorry. Yeah,
So-
the reactants and then
I mean, this
Okay,
this
so.
this end together, this end together. Is fine. You good with this? Okay.
Yeah.
But when you look up here, what the delta H one is NO2 plus N2O plus NO2 makes 3NO. When you calculate and you determine 2 N2O, 2 NO2 is 6NO.
Yeah.
So you have to divide
we can get into it
by 2.
because again, the one has
Yeah.
Divide this by 2.
Now it makes, oh, and then from here. Thank you, so. We add all these.
Yeah, I think so. Are you gonna explain it? Yeah.
I can.
Just,
Is there something you're stuck on?
just basic.
Is this desk higher? Should have a level change on it?
Sure. I was just looking at, you wouldn't match the first equation with the second,
No,
I guess,
because
because
yeah,
I was just thinking, because this has 2 and
You're
rather than,
better watch out for this. You have it's NO2.
yeah, versus this missing.
Oh, I see.
So if I put a 2 there, and then this multiple
Oh,
by 2.
this is what you want. That equation, that's what you want.
Yeah,
yeah, because you didn't
so alternate with.
So you don't want to flip this around. This is what you're looking for.
Oh, okay. Oh, that's what we're looking for. This is what we have.
Yeah.
I was just trying to balance it.
Yeah.
Okay.
With this.
Okay. I'm kind of concerned with individually.
For completion. Oh no.
That's fine. Okay, so the first one, this is on the wrong side, so this
Yeah.
is a reactant, it's on the product side, and that's a product and it's on the reactant side. So you flip it,
Yeah.
right? So that's the minus. So you flip it, you have a minus.
Oh, minus, yeah. But is that, how is that, those two would react to form that as well as a bilateral equation that it can go both ways?
Yeah, it can. I mean, but it's just like, I mean, it's like, even if it doesn't, you can still say it does, because delta H is path independent. So even if, like, I mean, although photosynthesis does happen, but it happens by a long process.
Yeah.
Right? So it's not like, I mean, you can form glucose from carbon dioxide and water, but it tries to do it. But it's very difficult. It's much easier to turn glucose and oxygen into carbon dioxide and water.
Yeah, okay.
Right? But either way, the delta H, like glucose burning, it
Yeah.
requires the same amount of energy as carbon dioxide and water to form
Yeah.
glucose and oxygen.
So that's the basic premise is energy.
Yeah.
That's what we're looking for. is
Yeah.
energy.
Yeah.
That makes sense.
And again, it's path independent, so you can do that.
Yeah. Okay.
So, I mean, like this part up here. I mean, you can't take carbon, hydrogen, and form propane. That's near impossible, right? At least not one product. You get a whole
Yeah.
bunch of things, right? But this is kind of a made-up thing,
Okay.
right? Okay, so this one is written like that, and then this one, since NO is a product,
Yeah.
you leave it on that. You leave it there, and since this says N2O is a reactant, you leave it on that side.
Yeah.
And now the next thing is, what do you multiply by? I think the easier way to look at this one is to get rid of these. So the N2's here, I'm going to multiply this equation by 2,
Yeah.
because then we have 2 N2's, 2 O2's, and 4 NO's, because then these two get 2 O2's, and these cancel there.
Yeah.
And then the N2's cancel there.
Yeah.
Right. And then if you add them up, you get this.
Okay, we can take them all.
Yeah. And then so those cancel. So now you have 2 N2O, 2 NO2's there,
Yeah.
and you get 4 plus 2, 6 NO's. but you want
Yeah.
this, so you divide by 2.
Yeah. That's how that comes into play. Awesome.
Does that make sense?
Yeah.
Okay.
Okay.
So something about thermodynamics is it doesn't have to make sense. That's the other thing. What I mean by that is like this equation here, the three carbons plus 4 hydrogens makes C3H8. I mean, come on, that's not going to happen. You can't throw carbon and hydrogen together and watch it react to form propane. I mean, you could, but you're not going to just form propane. You're going to form lots of other things, and it's more likely you heat it up, you're probably going to have other things happen. So this experiment, 3 C's plus 4 H2s to make C3H8, is pretty much not going to happen in a laboratory. But by the fact that H enthalpy is path independent, you can find out what the energy of that is by looking at these other steps. That's the other thing, is that the enthalpy H is a state function, and you can manipulate it out that way. So that's the other point with this here. Why am I doing this? How is that able to happen? It's because of the fact that enthalpy H is a state function, and it's path independent. So it doesn't matter what path you take to get there. In this weird way, I've taken it by multiplying these equations by equations and multiplying or adding them together and then dividing by 2. I can do that way. As long as I'm following everything properly, it's path independent, it'll work out fine. So, does that make sense? Anybody have any questions? The answer is C. I want to know what the answer is. So although I've gone around and talked to everybody individually. So questions with this? Is that the last? Okay, yeah, that's the last thing for this set of notes. So the last notes, we're going to talk about standard states. So you notice now that, so enthalpy, so H, E, and we'll later on talk about G and S, and maybe if you go to another class, you can talk about Helmholtz free energy. They're all path independent. They're all state functions. So what we've done is we've gone and taken a bunch of, we decided, you know what's an easy way to get everything done? Let's just pick standard states and then relate everything back to them. And this is kind of like having the smart student in class and then everyone copying his or her homework. Right? We've already gone through and we have all these standard states, and now we can relate things to standard states and then making the energy calculations very easy. So we're going to find our standard states, and this is the United States of America definition. It's very similar to the Russian Federation definition. We found this out that when we collaborated with them on the International Space Station, we had different standard states. I forget the temperature. The temperature might have been the same for Russia. I don't know if it was 25 degrees. United States is 25 degrees Celsius. Russian standard state was an atmospheric pressure of 1 bar. 1 bar is 10,000 kilopascals. So 101.3 kilopascals is an atmosphere. So I think the Russians had a better idea for their pressure. It's a much like nice round number, so 100,000 pascals, 100 kilopascals, whatever. But what we did, of course, in our typical diplomatic arena, we flexed our muscle and said, no, Russia, you have to adapt our standard states, and so they did. Russia now uses United States standard states, not their Cold War standard states. So I guess when you win the war, you get to check your standard states as well. Rewrite history and then have the standard, and rewrite thermodynamics. So here are standard states for a gas. Standard state at a pressure of exactly 1 atmosphere. For a liquid or solid, it is the most stable form at a pressure of 1 atmosphere, a temperature of 25 degrees Celsius. So what I mean by that is carbon. So carbon has a couple forms. There's graphite, there's diamonds, and then there's the fullerenes. There's C60, C70, and there's also nanorods. That's basically graphite. So what we pick as a standard state is graphite. That is the most stable. So Diamond is not the stable standard state for carbon. And actually, diamonds are unstable at this temperature and pressure. They will slowly turn back into graphite. For solutions, 1 atmosphere, 1 molar. Everything's at 1 molar for a solution. Okay, then the enthalpy change is when all reactions and products are in their standard states. And then the standard enthalpy of formation. So for a pure compound, the enthalpy change is then when everything is in its standard state. And then for an element, the standard heat of formation for an element is 0. And also I mentioned carbon. Carbon has multiple ones. We pick the 0. The 0 for carbon is graphite. It's not diamond. It's not C60. It's not C70. It's graphite. Same oxygen. Oxygen can exist as plain old oxygen atom radical. It can be as O2, the stuff that we breathe. It can be an ozone, O3. We pick the standard state to be O2, so the diatomic oxygen. And then the other ones are related back to it. So that's another thing about enthalpy H. Enthalpy H, it's a relative scale. So enthalpy H is a relative scale, and we relate things to zeros. And the zeros specifically are the elements, and we pick the most common stable element at terrestrial conditions. So we relate everything back to the most stable terrestrial, meaning here on Earth at the surface of the Earth conditions. And then we relate everything else to it. There are some things that are absolute scales. So temperature is an absolute scale. Also, entropy, which you'll learn about next semester, is an absolute scale. But enthalpy, free energy, that's Gibbs free energy, internal energy E, they're all relative. They're all relative. We pick the zeros. And we also pick the zeros to make the math the easiest. So we pick the zeros to be the most stable form, which makes, like I said, makes the math easiest. Okay, and here are some standard enthalpies. And I want you to memorize this chart. I'm just kidding. You don't have to memorize this chart. You always have your these data given to you. Okay, and the heat of reaction, so the delta H0 reaction. Oh, and if you see this degree sign there, that means standard state. So I know that I tell you some things, and I also told you degrees, like in degrees Celsius. That means it's a relative thing. That's also, it also means that. And then part of it is the zero reaction. You could argue that it's related as well, because you pick the standard states to be 0 for enthalpy. But this 0 in this case is the superscript. That means standard state. So the delta H0 reaction, the standard heat of reaction, is equal to the sum of the number of moles of products, the enthalpy of formation of the products, minus the sum of the number of moles of reactants, enthalpy of formation of the reactants. So this capital sigma, this means a sum series. Like for instance here, if you have the sum of n equals 1 to 5 of inverse n, this equals 1 over 1 plus 1 over 2, 3, 4, so on. This is a sum. This is capital sigma. There's also capital pi. This is known as a geometric series. So that's the same thing, but you multiply them together. So you might see this in other math classes. But we use this sigma notation very frequently. Sigma means sum. So let's apply this for this reaction. Use the enthalpies of formation to figure out the heat of reaction for this one here. So what is the heat of reaction for that one? So we apply this equation here. So let's do the products first. So delta H0 reaction is going to be the products 4 times the heat of formation of standard heat of formation of NO plus 6 times the heat of formation of water, gas, minus 4 times the heat of formation of ammonia plus 5 times the heat of formation of oxygen. Like so. So do you see I've applied that equation up there? We have the products for first, the N for NO is 4, the N for water is 6. So 4 heat of formation NO, 6 heat of formation water there. And then minus the sum of the reactants, 4 ammonias here, 5 oxygens there. So, is everyone good with that? Okay. One of these is a 0. Which one? I know this without even looking at it. Which one's a 0? Which one's an element? Oxygen. This one is a 0. So, how do I know that? Well, I can look up the chart. So, where is O2? O2 is right here. O2 is 0. How do I know it was a 0? The heat of formation for an element in standard state is 0. So that one is 0. Now we just have to put in the numbers. And the other thing, you notice I get kind of sloppy sometimes. I didn't put gases for any of them, but I did note that water is a gas. And the reason for that is because water gas and water liquid have 2 different heats of formation. So you have to make sure you have the right heat of formation on there for the right state. Okay, so now we just have to put the numbers on there. Okay, 4 heat of formation of NO, heat of formation, where is nitrogen? Sulfur, oxygen, where is nitrogen? Oh, there it's right there. NO is 91.3. 91.3. It took me a while to find it. It's right here. 91.3. Water gas minus 241.8. Is that right? Was it 241.8? Yep. Minus 4 times ammonia. Ammonia is here, 45.9. And oxygen, O2 is 0. So now we just have to put it in our calculator. 4 times 3 minus 6 times 8. And I get minus 902. Like that, and if you're wondering where the per mole comes in, it's per mole reaction, meaning the entire reaction as written. That's where the per mole comes in. So this one here, how do you do the standard heat of reaction for this reaction? you look up the heat of formation of each of these, and you do the products, sum of the products, moles of products minus the reactants times moles of the reactants, and you look them up, oxygen is 0, and you get minus 902. So, questions with this? Now one thing about thermo, this is so easy. We haven't done any of these experiments yet. Do you know how hard it is to get these values, to sit there and measure out the temperatures? It's really, really hard. And with experimental error, you have to do it over and over again, and you have to get the right things. And if you want to do it on the fly, you might be able to get a decent one, but it's still difficult. Instead of that, by taking various things, applying Hess's law on all sorts of things, right? We showed you Hess's law to find right here the C3H8. That's the heat of formation of C3H8. We had to use Hess's law for that. Someone has already gone through and applied Hess's law and applied all these things and figured out the standard heats of formation for everything. And now all you have to do is apply the equations, and you can get the energetics of any reaction that you want. So we've basically solved a huge amount of things that are already needed to be figured out, and it's easy. Now, so that's one thing about thermo, is a lot of it is already figured out. Although there's still more that needs to be figured out. There's always new and amazing compounds being formed, new drugs being formed, the energetics that we need to figure out for there. But just about anything, if you want to figure out how much energy you need to put in to form steel from iron ore, we can get that pretty easily. So let's do this equation. Does anybody know the name of this reaction? 2 aluminums plus iron oxide makes aluminum oxide and iron. This is known as a thermite reaction. And the heat of formation I've listed there. What is the heat of reaction here for the thermite reaction? Let's see if you can figure this out. Anyone ever heard of something called the Hindenburg before? Never heard of that before. Oh wow, I don't know the history. It was a Zeppelin, a Zeppelin, kind of like a blimp. We have blimps here in the United States, Zeppelins, and I don't know the difference between a Zeppelin and a blimp. I know that in Germany they used hydrogen. So as a form of transport, the Hindenburg was a Zeppelin. So it was, I don't know, I think of it as a blimp. Anyways, United States, all this for warfare. We still have a huge hoard of helium. So we have a strategic supply of helium. We actually were ordered by Congress, well, the U.S. military was ordered by Congress to get rid of its strategic supply of helium. So helium is extremely cheap. And until it runs out, then it's going to become very expensive. And we hoarded helium because of U-boats. And what happened was the blimps used to follow flotillas of ships. And so let's say a U-boat would come, a submarine would then fire torpedoes and sink boats in the flotilla. What would happen was the blimp would follow the submarine and then wait till the submarine had to submerge because submarines back then, they were diesel powered. And they had to surface and then recharge their batteries. So what would happen is when the submarine surfaced, the blimp would then bomb them and sink the sub. So a blimp was a strategic part of a naval flotilla. And the United States didn't want Germany to have the ability to do this, so we hoarded all of our helium. And Germany wanted to use blimps, but they couldn't do it with helium, so they used hydrogen, and which is in fact lighter than helium. Then the Hindenburg came along, and they had solid aluminum frames, and they had paint that had rust on it, so red paint is rusty. And then the blimp itself, the inside of it had hydrogen. And what happened was they determined by an electric discharge, there was enough activation energy to start the thermite reaction, which then ignited the hydrogen inside of the blimp, or the Zeppelin, and then the whole thing exploded. So, and a bunch of people died. And surprisingly, it was the ones that jumped out died. The ones that stayed in the burning inferno, some of them survived. But, so no, you guys haven't heard of this. I'll show some pictures after, so you know that I'm not full of fiction. Okay, so what is the heat of reaction for this one? Actually, I don't need that. Okay. How many think it's A, negative 850? I think it's B, 850. I think it's C, negative 2500. D, okay. Guys aren't playing. Okay, which one's the product? Well, the iron and aluminum, they're both elements. They're 0. What's the product? Is it Al2O3 or Fe2O3? Yeah. Okay, Al2. Okay, the product. So the delta H 0 reaction. No. Are you guys getting tired? Is that what it is? Lab and the Hess's law wore you out. So that's the equation. So an aluminum is minus 1600 and iron is minus 800. So minus 1600 minus a minus 800 is about negative 800. Right, so answer is A. So the thermite reaction, this is a very violent reaction. Let me see, I think I might have this in, I should have looked at this before. My reactions. There we go. Chemistry in action. Do I have that with iron? Oh, here we go. This is a thermite reaction right here. So that's the iron oxide rust and powdered aluminum. And there's a sparkler. Provide the activation energy. It's very reactive. They use these as grenades as well. They have thermite grenades as a weapon in warfare because it's very exothermic, so you can use it to melt things. They can use it as anti-tank. Some of them are anti-tank grenades. Okay, so that's... They can use them to weld things together. Oh, let's look at the Zeppelin. Siri, do you have pictures of the Hindenburg? Pictures of the Hindenburg. FaceTime Lisa. What's I love you in French? That's J10. Come on, I know that. Pictures of the Hindenburg.
I couldn't find any matches in your photos library.
Oh, no
Here are
crap.
some images.
There you go. There is the Hindenburg explosion. Thermite reaction, then... Oop. Oh. Thermite reaction, then exploded hydrogen. Okay. So questions on this? All right, good. We're done with thermo. Whew. We can enter quantum mechanics. I love quantum. Has anyone heard of Schrödinger's cat before, out of curiosity? Oh, we got one person. Talk a little bit about, well, there's if you study the history of science, there's a lot of scientists that are outright jerks. Okay, I mean, some of them I'd like to punch in the face if I could, like Heisenberg. That guy he just looks like a jerk if you look at his picture. Haber, another jerk. Heisenberg, well, I guess he wasn't himself a Nazi, but he wasn't, well, he did and said some things that were bad. Same thing with Haber, although he did a lot of good things. He was a pioneer. He was the first one to develop chemical weapons. So, but Schrodinger, on the other hand, Schrodinger is, if you have one of those questions, you ever had one of these breaking the ice questions, who would you like to have lunch with? You know, name any people, like 3 people, dead or alive, you want to have lunch with. I probably wouldn't pick Schrodinger, but because there's a lot of the more interesting people I like to meet. But if I could be friends with any scientist in the past, it's probably Schrodinger. He was an incredible guy. I got to listen to his voice. He won a Nobel Prize, and if you go to the Nobel Museum in Stockholm, Sweden, they have like videos of all the Nobel laureates. And there's just something about Schrodinger, the way he talked. He has this electrifying voice. You know, it'd be amazing to see him in a lecture. A lot of like Faraday, Michael Faraday. He was an amazing speaker. There's just something electrifying about Schrodinger. But Schrodinger was a physicist, and he was really good with waves. And this is we are trying to figure out how electrons work. And Schrodinger figured out the hydrogen atom exactly, and he did it in like a weekend. And because he went to this conference, and they're trying to figure out the energy levels of the hydrogen atom, and then he thought, this sounds like my wave equations, and he went away for the weekend, and he solved it. And he was frustrated, so Schrodinger's cat was, and part of things, when you look at things really, really small, they change versus classical mechanics. So right now, we're in classical mechanics, meaning I'm here. Now I am here. I'm not here and there at the same time. That's a very classical mechanical kind of thing. When we talk about electrons can be here, there, all over the place at the same time. So we'll talk about it in the future. And as Schrodinger was doing the math of this, he said, this is like if I had a machine that I had a cat in the box, and if I opened the box, there was a chance that this hammer would go down and hit and gas the cat. But it was a random chance, but only by me opening the box could I have this contraption work. But it only worked half the time. And when I observed the cat after I opened the box, either they're going to be dead or alive. But it's only after I open the box can I observe the cat. So, but what do I do when the box is closed? If I can't observe the cat being dead or alive, what state is the cat in? That's his way of explaining things like the spin of an electron. The spin of an electron can be up or down, but it can also be a superposition. It can be both. So he was trying to figure that out, and that was it's kind of a morbid example, I think. But his point was, when we probe something, when we analyze something, it changes its behavior, and it behaves in a different fashion. So for electrons, if you expect electrons to behave like waves and you observe them you try to observe them acting like waves, they'll act like waves. If electrons, you want them to act like particles, they will act like particles. Say, I want to see particle-like behavior of electrons, it will act like a particle. If you want to observe it as a wave, it'll act like a wave. So what is it that when you're not observing it? Like, well, it's kind of both. And we'll get to that. And this is like my starter, like, which door did you enter today? I came in the back. And you're probably the same, maybe you all came in the back too, maybe you in the front. You're like, well, this makes sense. If we were electrons, you'd be like, well, come on. We came in both doors at the same time. You know, oh, wait, I came in one door. I'm like a particle today. Like, well, the other one's like, I'm like a wave. I came in both doors. Electrons can behave that way, and it's kind of weird. I think this stuff is really cool, the quantum stuff. Okay, so the quantum mechanics applies to a thing. I should back up. There are, right now with physics, we know the accepted forms of physics right now are general relativity and quantum mechanics. And actually, they don't always overlap. General relativity replaced mechanics, so that's Isaac Newton. Isaac Newton's mechanics, gravity, that kind of stuff. It was replaced by Albert Einstein's theory of general relativity. And then quantum mechanics, this describes things that are really small. So we can use relativity to explain things like the orbits of stars and planets, and then we can use quantum mechanics to talk about things of the atom, the energy levels, and the nuclei, and electron clouds of atoms. But we cannot start with protons, neutrons, and electrons and come up with the orbit of the moon around the Earth. We don't have that ability to start small and get big and explain everything that way. We don't have the linkage between those theories yet. There are some proposed theories like string theory, although it's not a scientific theory, it's a mathematical theory. There are other competing theories right now like brain theory and M theory and these types of things. If you want to learn more of that, you can read Stephen Hawking's books. I like those books, but they talk a little bit more about that. But we're not going to talk about that in this class. We're going to stick to Intro to Quantum Mechanics. And it's a model. Quantum mechanics is a model. It's a very good model, but in and alone itself is a model. Light and electromagnetic radiation also follows quantum mechanics. And if you're wondering what electromagnetic radiation is, it is the carrier of the electrostatic force. So the fundamental forces, gravity, electromagnetic, electrostatic, however you want to call it, nuclear weak and nuclear strong. So it is the carrier of the electromagnetic force, and it has a ultimate particle. Well, it's not even a particle, it's energy. We call it a photon. And photons have both particle and wave-like behaviors, but we're going to stick to the wave-like behavior for now. So photons and electromagnetic radiation, they have an oscillating perpendicular electronic and magnetic field. So B means magnetic and E means electronic. So meaning if you have some sort of radiation, so like a radio wave traveling in this direction, it's a transverse wave, the electronic field is going up and down. So this is the electronic field. And the magnetic field, so if it's this plane, the magnetic field is perpendicular to that, going this way. So you have alternating, oscillating electronic and magnetic fields, and it's perpendicular to the motion. So the electronic and magnetic fields are perpendicular to each other and the direction of the motion. 3 dimensions is fine. Waves going this way, E field's going this way, B field is magnetic field is going this way. And they zero out the same spot. And they all travel at this for the radiation, electromagnetic radiation travels at the speed of light. And some terminology here. So if you look at a wave, the height of the wave is the amplitude of the wave, and then the length of the wave, you can do it from peak to peak, trough to trough. So the top is called the peak, the bottom is called the trough. Or you can do the entire wave from one going that way. Either way, that distance is called the wavelength. It's how long the wave is. And we'll learn about this soon, but red light has longer wavelengths and violet light has shorter wavelengths. So, and speed is the speed of a wave. This is just a simple physics, common sense thing. Speed of a wave is its wavelength times its frequency. So what is frequency? It just means how often you have it. Like what is your eating frequency? My eating frequency is at least 3 times a day, breakfast, lunch, dinner. So I tend to have a 3 times a day frequency for eating. So frequency just means how often you do something. For a wave, it's how many wavelengths do you have, and it's also per time. So my frequency of eating is 3 times per day. A frequency is like 1,000 times a second. Or like in an engine term, you have revolutions per minute. That's a frequency. That's how many times something happens per unit time. So if we have a frequency, how many times per unit time times the wavelength, so how often something happens, and then how long it is, that equals speed, right? So meaning that so if I have a wavelength of 1 meter, so a wavelength of 1 meter, and that happens 10 times a second, that's a really slow, that'd be like an ocean wave. 10 ocean waves a second, and they're all 1 meter long. How fast are these waves moving? Well, they're moving at 10 meters a second. So if we're going to have a wave come through 10 times a second, and each wave is a meter long, that means these waves are moving at 10 meters a second. Does that make sense? That's kind of should make it's common physics sense. So same thing with light and electromagnetic radiation, but it moves at the speed of light. Speed of light is 3 times 10 to the 8 meters per second, so 300,000 kilometers a second, 186,000 miles per second. So very fast. And the speed of light is constant. This is that's special relativity. Maybe you've heard of special relativity before. The idea is that with special relativity, that the speed of light is constant. So the speed of light is constant. Speed is distance divided by time. Time is the variable. So that's with the special relativity. Meaning, if you're in a car and you turn on a flashlight in your car, or the headlights in your car, if you're in a car and you throw a baseball, right? So if I'm in a car and I'm in the back seat and I throw a baseball to my older brother in the front seat, I see that baseball is moving at, 20 meters a second. Okay? If my car is moving 50 meters a second, and that's pretty fast, and then my father is outside the car looking at me throwing the baseball at my brother, he would see that baseball moving at 70 meters per second. That would be the speed of the car plus the speed of that inside the car. So you have 2 different reference frames. The question is, what about if I have a flashlight in the car or the headlights in the car? If it's moving at 50 meters a second, does that mean the light is moving at the speed of light plus 50? And the answer is no. And as you speed up, your time changes. So if you're in a car and you're moving faster than someone on the ground, you are moving, so that means that the person inside the car, his or her time slows. So that's relativity. Anyways, let's go back to this. The speed is all the same, and the frequency then. Frequency is obviously the red has longer wavelengths and violet has shorter wavelengths, higher frequency. If you were in a boat and there was a storm, which storm would be more dangerous? The red line or the violet line? The violet, yeah. Higher frequency means more energy. So that also, just you can look at it, you can figure that out. Is my shut-off alarm? Oh, there it goes. There's my shut-off alarm. All right. And we will cover more of this next time.